Hello, nice to meet you all again. Did you know that scientists at the Large Hadron Collider have created the hottest temperature ever recorded? A blistering 5 trillion Kelvin? That's hotter than the core of the sun. Meanwhile, the coldest temperature humans have achieved is an astonishing 38 picokelvin, equivalent to negative 273.15 degrees Celsius or negative 459.67 degrees Fahrenheit, nearly absolute zero. But could anything surpass these extremes? What makes one thing hot and another cold? Why do some objects feel warmer than others? And what is absolute zero? Why is it precisely minus 273.15 degrees Celsius or minus 459.67 degrees Fahrenheit? Buckle up as we embark on a thrilling journey to unravel the enigma of absolute zero and explore the frontiers of temperature. At the heart of the universe lies energy, the invisible force that powers everything, from the orbit of planets to the flicker of a candle flame. According to Einstein's iconic equation, E equals mc squared, even matter is a form of energy. Within matter, energy reveals itself most vividly through temperature, something we encounter every day, whether it's the warmth of a cozy blanket or the chill of an ice cube. But have you ever wondered why hot coffee and iced tea, both made of the same molecules, feel so different? The answer lies in the dance of atoms. Every molecule in matter is in constant motion, vibrating even in the most rigid objects like a steel rod or a diamond crystal. In physics, kinetic energy, the energy of motion, defines temperature. The faster molecules move, the higher the temperature. When molecules gain energy, they vibrate more intensely, breaking free from their bonds. This is why ice melts into water, water boils into steam, or metals turn molten under intense heat. But what happens when we reverse the process and cool things down to the extreme? Humans have long been fascinated by temperature, but understanding and measuring it wasn't always easy. Why is it simple to heat something up, like boiling water over a fire, but so challenging to cool it down? You can boil water to 100 degrees Celsius with just a campfire, but try cooling it by 10 degrees Celsius without a refrigerator. Nearly impossible. Only in the last century, thanks to breakthroughs in science and technology, have we begun to conquer ultra-low temperatures. But why is cooling so much harder than heating? Here's another puzzle. When we measure length, mass, or time, we use positive values. You'd never hear of minus 5 meters or minus 1 kilogram. It sounds absurd. Yet negative temperatures like minus 10 degrees Celsius feel perfectly normal. Why is that? To answer this, let's travel back in time to see how humans first tackled the challenge of measuring temperature. In 1714, German physicist Gabriel Fahrenheit, a self-taught genius, crafted one of the earliest temperature scales. He chose 0 degrees Fahrenheit as the coldest point he could achieve by mixing water, ice, and ammonia. His second reference was human body temperature, set at 96 degrees Fahrenheit. By dividing the range between these points into 96 equal parts, he created the Fahrenheit scale. In this system, water freezes at 32 degrees Fahrenheit and boils at 212 degrees Fahrenheit. This scale is still used in places like the United States, but it's not the global standard. Fast forward to 1742, Swedish astronomer Anders Celsius proposed a more intuitive system. He used two natural benchmarks, water's freezing point at 0 degrees Celsius and its boiling point at 100 degrees Celsius, dividing the range into 100 equal parts. The Celsius scale's simplicity made it the go-to choice for most of the world. But both Fahrenheit and Celsius scales are practical tools for daily life, not the full scientific picture. To truly understand temperature, scientists needed a scale that reflects the fundamental nature of matter, the Kelvin scale. The Kelvin scale is unique because its 0 point, known as absolute zero, is where molecular motion theoretically stops. Absolute zero is negative 273.15 degrees Celsius, or negative 459.67 degrees Fahrenheit, and unlike other scales, Kelvin has no negative values. But what makes absolute zero so special? Temperature measures the average kinetic energy of molecules. As you heat something, molecules move faster, increasing the temperature. As you cool it, they slow down. At absolute zero, theory suggests that all molecular motion would cease. But here's the catch. It's impossible to reach absolute zero. Why? The Heisenberg uncertainty principle in quantum mechanics tells us that particles can never be completely still. They always retain a tiny amount of energy, called zero-point energy. This makes absolute zero an unattainable limit, like the speed of light. The concept of absolute zero emerged from a key discovery in 1802 by French chemist Joseph-Louis Gay-Lussac. He found that at constant pressure, the volume of a gas changes proportionally with its temperature. Specifically, for every 1 degree Celsius drop, the volume decreases by 1/273rd of its volume at 0 degrees Celsius. If you keep cooling to negative 273.15 degrees Celsius, the volume would theoretically become zero, an impossible scenario, as matter cannot simply vanish. This led scientists to identify negative 273.15 degrees Celsius as the ultimate lower limit of temperature, absolute zero. This discovery inspired the Kelvin scale, where 0K marks this theoretical boundary. But why exactly minus 273.15 degrees Celsius? It's a question that echoes other mysteries of the universe, like why the speed of light is exactly 299,792,458 meters per second, or why an electron has its precise mass. These are fundamental constants, rules of nature we can observe but not fully explain. Absolute zero is one such cosmic rule, defining the limits of how cold the universe can get. At ultra-low temperatures, incredible phenomena emerge, revealing the strange world of quantum mechanics, superconductivity. When cooled to near absolute zero, certain metals like mercury or lead lose all electrical resistance. This means electricity can flow through them forever without any energy loss. Imagine power lines that never waste energy or magnets that levitate trains. This is the promise of superconductivity, already used in MRI machines and maglev trains. Bose-Einstein condensate, BEC. In 1925, Albert Einstein and Indian physicist Satyendra Nath Bose predicted a new state of matter. It wasn't until 1995 that scientists, led by Eric Cornell and Carl Wieman, created a BEC by cooling rubidium gas to a fraction above absolute zero. In this state, atoms synchronize and act as a single superatom, displaying quantum effects on a visible scale. For example, a BEC can slow light to a crawl, down to 0.2 millimeters per second, compared to its usual speed of 300 million meters per second. This phenomenon could revolutionize quantum computing and precision measurements. While we can't reach absolute zero, getting close has transformed our understanding of the universe. Superconductors power advanced technologies like particle accelerators and medical imaging. BECs might unlock the future of quantum computers, capable of solving problems beyond the reach of today's technology. As we push the boundaries of what's possible, discoveries at absolute zero may one day bring us closer to the infinite absolute, a future where the mysteries of the cosmos are within our grasp. Stay curious, and let's keep exploring the wonders of the universe together.